So our next speaker for the session is Koji Yamaguchi. He is a postdoc here at the University of Waterloo. Did his PhD at Tohoku University with Masahiro, actually. So Koji is going to talk about entanglement is better teleported than transmitted. Koji, whenever you want, the floor is yours.
Okay, thank you for the introduction. So today I will explain our work on the efficiency of transmission of entanglement through a quantum field. And this work is done in collaboration with Atom Kemp, and the paper will appear on arXiv soon. So in this study, we investigate the transfer of entanglement through a quantum field. And such a transfer of entanglement can be very useful, for example, in order to create a large quantum memory by combining modules of small quantum memories. So suppose that we have a small quantum memory, and one promising way to construct a larger quantum memory is to combine many such small memories. And if the modules are connected only by classical channels, then no entangled state can be generated. And therefore, to fully access a large Hilbert space of the combined small quantum memories, we need a quantum channel, and the entanglement must be spread across the modules at will. And to analyze such a communication scenario, we consider the following simple setup. Suppose that Alice has a qubit A, which is initially purified by an ancillary system A tilde. And this A tilde could be a part of single module or can be spread over multiple modules. And a receiver Bob has a qubit in another module. And we assume that A tilde is inaccessible to Alice and Bob, and they collaborate to create entanglement between A tilde and B by communication through a quantum field. In other words, Alice tries to transfer entanglement between A tilde and A to Bob. So this is the situation we consider. And concretely, we analyze two different setups. In the first setup, Alice and Bob simply couple their qubits to the field. And the field disturbance caused by Alice propagates through the spectrum, and which is later picked up by Bob. And as a consequence of such a communication, B can be entangled with A tilde. So this is the transmission scenario. In the second scenario, we consider quantum state teleportation combined with entanglement harvesting or generation. In this scenario, Alice and Bob first share entanglement through the interaction with the field, and they implement quantum state teleportation by consuming this entanglement. And in both scenarios, we use the negativity between A tilde and B as a quantifier of the efficiency of communication. So let us start with the transmission scenario. So here is the detail of the setup. Initially, A is assumed to be purified by A tilde, and the qubit B and the field are in an arbitrary state. And the interaction Hamiltonian we consider is given by the sum of two contributions, where HA is the interaction between A and the field F, and while HB describes the interaction between B and the field. And we do not import any further assumption for the detail of the interaction Hamiltonian, except for the assumption that those Hamiltonians have a perturbative parameter lambda, which can be understood as a coupling constant. And due to the interaction, the state evolves into this equation here, which can be expanded as a perturbative series with respect to lambda. And for such a general setup, we found a no-go theorem. For any initial state and the interaction Hamiltonian, it is shown that the negativity vanishes to the second order of the coupling constant. So this result is derived by using the ordinary perturbation theory of eigenvalues. So here this is the first main result of the paper for the first setup, I mean the transmission setup. In the transmission scenario, no negativity can be transmitted from Alice to Bob to the second order of the coupling constant. So now let's move on to the second scenario, where we consider the teleportation combined with entanglement harvesting. But before explaining our setup, let me briefly review the standard quantum teleportation scenario. This protocol is composed of 4 steps. First, Alice and Bob share a maximally entangled pair of qubits, which we call A prime and B. And then Alice performs a barrel measurement on A and A prime, and the measurement result is communicated to Bob. And depending on the measurement result, Bob performs a local unit operation, in this case, the powder operation. It can be easily shown that the final state of A tilde B is equal to the initial state of A tilde A. So this means that by consuming an ideal entanglement resource, that is the Bell state in this case, the state of A is perfectly transmitted to B, including correlation with A tilde. And in our protocol, instead of such an Bell state, we use entanglement generated through a quantum field. And in order to clarify the setup, let me briefly review entanglement harvesting here. In the common setup of entanglement harvesting, we consider 2 qubits, which are linearly coupled to the field. And we call these qubits A prime and B. The interaction Hamiltonian between a qubit and the field is given by this equation, where lambda is the coupling constant and chi is the so-called switching function that characterizes the duration of interaction, and mu is the monopole moment, and the f is the signaling function that characterizes the spatial extent of the detector. And when the detectors are initially in their ground state, and if the field has vanishing first moment, then the reduced state of the qubit are perturbatively given by this equation. And the detailed definition of L, Lij, and M are not used in the following discussion, but the important thing is that there is a closed formula to characterize the negativity perturbatively in terms of M, L and M. And by combining the entanglement harvesting and the quantum state teleportation, we propose the following protocol. In the first stage, Alice and Bob harvest entanglement through interaction with the quantum field. And then Alice performed a Bell measurement on A and A prime system, and the measurement outcome is transmitted to Bob. In the last step of this protocol, Bob performs a local unit operation depending on the outcome mu. And the unit operation he performed is very similar to the standard one, but it contains some phase shift operation. And in our protocol, the final state of A tilde B is given by a somewhat complicated equation here. Here, P is the Schmidt coefficient of the initial state of A tilde A, and psi and psi prime and phi prime are the bases appearing in the Schmidt decomposition. And for system A, we have 2 different bases in general. One is phi prime, which appears in the Schmidt decomposition of the initial state. And the other one is the basis phi, which appears in the definition of Bell measurement. And in the case where these bases are the same, we found a closed formula for the negativity between A tilde and B. Here, L and M are the parameters defined in entanglement harvesting, and P is one of the Schmidt coefficients of the initial state of A tilde A. And from this formula, we can see that, for example, if P is 0, the negativity vanishes. And this is expected because if P is 0, A tilde A are not entangled at all. So this means that after the protocol, A tilde cannot be entangled with P. Okay. And since the negativity is entanglement monotone, it should decrease under any LOCC. And since our quantum teleportation protocol is LOCC, the negativity must vanish. And to check this fact, we compare the transfer negativity, this one, and the harvested negativity. And we found that in general, the transfer negativity is less than or equal to the negativity consumed in the teleportation protocol. And in particular, we find that the equality is attained when two detectors in the entanglement harvesting are identical, and A tilde A are initially maximally entangled. So this implies that our protocol is optimal in this perturbative regime, in the sense that the maximum possible amount of negativity is teleported. So here is a summary of my talk. We consider the transfer of entanglement through a quantum field, and we investigated two different scenarios. Okay, 2 minutes, yes. And so in the first scenario, we consider transmission where a field plays a role of media of communication. And in this case, for any interaction Hamiltonian and the initial state, no negativity can be transferred to the second order of coupling constant. In the second scenario, which we call teleportation setup, the field plays a role of source of entanglement. In this case, we found a formula to calculate the teleported negativity. And under some condition, we show that our protocol is optimal in this perturbative regime. So the important thing is that in the second case, the negativity can be transmitted in the second order of coupling constant. So the entanglement is better teleported than transmitted. And also, our results suggest that it is essential in communication through a quantum field to understand the properties of the quantum field, not only as a media of communication, but also as a source of entanglement. Thank you very much.
Thank you very much, Koji.
So you may need to put your slide up. I just want to be sure I understood this and what you meant when you say it's better teleported. So my understanding of this is A and B harvest some entanglement, and then A, if you like, teleports, basically swaps the AB entanglement is swapped with the A prime or A tilde B entanglement via teleportation. Is that the basic idea?
Yes. So our idea is to make use of harvested entanglement, and by consuming such an entanglement, we implement the teleportation protocol. And in an ordinary teleportation protocol, we use the pair state as a resource, as an entanglement resource, right? And since we are using the noisy resource, we cannot perfectly transmit the information, but we show that some negativity can be transferred to both.
Okay, so like I guess you say, like, what other options are available? You say it's better than transmitting, but can you explain that a bit more? Like how?
So the reason. Okay. So the reason why I said better is in the transmission scenario, even if we try to optimize the interaction or the initial state, we cannot transfer any negativity to the second order of the coupling constant. This is one of our.
If you are time-like, if you're time-like, you can, right?
No. Even if it's time-like, to the second order, to the second perturbative order, we cannot transfer negativity.
No, you can. You can get two detectors entangled through strictly, not harvesting, strictly communicating, for sure. At second order, you have a lambda A, lambda B contribution. It's the same contribution used to communicate that can also entangle, indeed, yeah.
I agree. So we can make A and B entangled to the second order coupling constant. But what we want to do is transfer entanglement with auxiliary system A tilde. And what I am claiming is that we cannot make A tilde entangled with B through the interaction, I mean the transmission.
Okay.
So, well, this is what I'm trying to understand. So you're saying that if A and A tilde were entangled, then you can't transfer that to B to order lambda squared. But via the harvesting thing, you could.
Yes.
Okay, all right. That's the part I missed. Thank you.
Okay, thank you very much.
Thank you. I missed it too. Thank you, Rob, as well.
Thank you very much for the question.
All right.